To start with, I would like to introduce you to the topic generative adversarial networks by breaking down the terms generative, adversarial, and networks. Let's assume that you are solving a deep learning problem and you have a limited set of data, but the complexity of the problem requires more data in order to make more accurate decisions. Wouldn't it be nice to have a neural network that generates the related data out of already available samples in order for you to run your code on it? Well, this type of model is referred to as generator models. The idea behind generative modeling is that we have a collection of training samples, usually of high dimensional samples such as audio waveforms or images. Such data is hard to collect through conventional means. The adversarial training models arose when researchers were facing worst case scenarios and worst case inputs either by another model or by an optimization algorithm. Adversarial models, when used separately for the outputs of other models or optimization algorithms, would not benefit us as much as applied together in the same network, because the feedback of generative model tends to enhance the performance of adversarial and vice versa. GANs was first introduced by Ian Goodfellow in 2014. This idea was later adopted by many researchers, and those researchers used it in different domains of image generation, video, poems, and simple conversation generating. Now let's talk about the constituents of GANs. In the context of generative adversarial networks, both key players are the neural networks, and the goal is to learn to generate data that resembles with the data in the training set. GANs, unlike other models, not only does the adversarial job for the generated data, but also sends feedback signals to generator model, and when the generator model gets updated to do a better job, so much so that it can easily deceive discriminator that does the adversarial job. The later is updated to enhance its performance. Thus, a coupled system is formed that during learning phase matures performance of both competing neural networks. Now let's talk about what are the motivations behind GANs. A famous physicist scholar has a saying, "What I cannot create, I cannot understand." Since artificial intelligence is believed to have a phenomena of understanding, the process the phenomena of understanding the process systematically, this aspiration has led AI to a new level of generating and evaluating outcomes. Those outcomes can either be of its own models or they can be generated by some generator, or they can be you know related to some reference data. With the rise of computational power and demand in data required to train AI algorithms, the researchers came up with the idea of combining the learning stage of algorithm with its ability to generate similar data by making variations in the actual data. Therefore, in generative adversarial networks, two neural networks compete with each other, where generative networks tries to add similar samples as given in the training data, and adversarial network evaluates if the data belongs to real or fake. Here the adversarial networks gives you the output 0 or 1 based on its prediction that whether the data that was passed to the adversarial network belongs to some generator, or whether it belongs to the actual data that you provided. So next is the adversary role in GANs. We have discussed extensively the generator's role in generative adversarial networks. Now we are discussing the adversary role in GANs. The GANs methods converts the problems of unsupervised nature to a relatively supervised problem. Why do we say that it's a relatively supervised problem? Because the nature of the data that was provided to the generator was of an unsupervised nature. But the nature of the data that was given to the adversarial networks, we call it a discriminator network. It was of a supervised nature because you fairly have the idea that which data was provided to the generator and which data was provided to the was created by the generator. The actual data that is provided to the generative framework is of unsupervised in nature, but the data provided to adversarial network is supervised. The prediction of the adversarial network is either true or false based on the judgment against the data, indicating whether it belongs to the actual data or the data created by generative network. The idea of GANs comes from a two-participant game where one player tries to deceive the other player and the other player is striving to catch the deceptions created by the first player. Same is the case with generative and adversarial networks. If the generator at any point can easily deceive adversarial network, the network needs to be updated. And this is the case of vice versa. Because if generator can fool discriminator so easily, the discriminator needs to be updated. Or if the discriminator is acting in a way that it can easily predict the outcome of generator and classify that whether it was coming from output of a generator or it belongs to the actual data, then the generator is to be updated in a way that it uh, generate better samples that are more deceivable for uh, the discriminator network. Because these two act in an opposite way, this gives two different and opposite optimization goals to both the networks, and hence the network at large adopts to not only learn but evaluate its outputs to do better. Now let's look at some functional explanation of GANs. The main idea of GAN comes from Nash equilibrium in the game theory. As we discussed in the previous slide, it assumes that there are two game participants. One we call it the generator and the other we call it the discriminator, and these both are neural networks. The generator aims to learn the distribution of real data, while the discriminator aims to correctly determine whether the input data is from the real data or the generated data. Sorry. The computation procedure and the structure of GAN is shown in the figure. Any differentiable function can be used as the generator and the discriminator. Here we use differentiable functions d and g to represent the discriminator and the generator, and their inputs are real data x and random variable z. G of Z represents the sample generated by G and obeying the distribution P of data of real data. If the input of discriminator D is from the real data X, D should classify it to be true and label it as 1. The input, if the input is from G of Z, D should classify this to be false, and label it as 0. The purpose of discriminator D is to achieve correct classification of the data source, while the purpose of G is to make performance of the generated data G of Z on D, that is D of G of Z, consistent with the performance of real data. The real data is X on D, that we call here as D of X. The adversarial optimization process improves the performance of D and G gradually. Eventually, when the discrimination ability of D has been improved to a level, but it cannot discriminate the data source correctly, it is thought that a generator G has captured the distribution of real data, meaning when the generator is improved to a point where it generates such data that it's very hard for discriminator to understand that it was a real data or the data generated uh, data generated by the generator network, then the generator performance is considered to be maximized. Now let's talk about a little bit about learning method of GAN. First, we describe the optimization of discriminator D given generator G. You see here the optimization and learning of generator and discriminator are interchangeably dependent on each other. Similar to the training of sigmoid function based on classifiers, training the discriminator involves minimizing the cross entropy. Next, we have the loss function, where objective of D given theta D and theta G, where theta G and theta D belong to the discriminator and uh, the generator networks, where X is sampled from real data distribution P of data of X, Z is sampled from prior distribution PZ of Z in such a way that it is uniform or Gaussian distribution, and E represent the expectation. It's noteworthy that the training data consists of two parts. One part from the real data distribution, which is given as P of data of X, and another part from generated data distribution that we talked about earlier, P of G of X. This is slightly different from the conventional methods for binary classification. Given the generator, we need to minimize the equation given at first to obtain the optimal solution. In a continuous space, the equation given at 1 can be reformed as the equation given at the second point. Now you can see for any m and n belonging to real numbers, the expression becomes same as minus m log of y minus n log 1 minus y. This equation achieves its minimum value at y is equal to m over m plus 1. Hence, given generator G an objective function given at the second equation, the objective function becomes d of g of x is equal to P of data of X divided by P of data of X plus P of G of X. This is the optimal solution of discriminator D from the last equation. On the other hand, D of X denotes the probability of X sampled from real data rather than the generated data. If the input data is from real data X, the discriminator strives to make D of X approach. But if the input data is from the generated data G of Z, the discriminator strives to take D of G of Z approach. While the generator G tries to make the approach, and we have uh, expected it to be a zero-sum game between G and D, where they both are a competing neural network and they have opposite but the same optimization goals. The loss function of G would be equal to objective of G of theta G is going to be equal to minus objective of D of theta D or theta G, which is given at second equation. So it's the optimization goal of the generator is going to be inverse of the optimization goal of the discriminator. In order to summarize this, for learning the parameters of GAN, we need to train the discriminator D to maximize the accuracy of discriminating the input data from the real data X or the generator data G of C. In addition, we need to train the generator G to minimize log 1 minus D G of C. Now let's talk about some GANs examples where generative adversarial network is used. There are a bunch of examples where a generative adversarial network was used, and some of it are given below. The SEQ GANs, SEC GANs, these GANs, they were connected with reinforcement learning. In reinforcement learning, here you can see the generative adversarial networks are sort of behaving like the reinforced approach, because the output of the discriminator D tries to improve the performance of generator G, and the output of the generator G tends to enhance the performance of discriminator D. So this approach was used in SIG GANs. The next is MAL-GANs, and these GANs algorithms were used to generate adversarial malware examples. The next example of GANs is ST GANs, where the generative adversarial net framework was used for style transfer, which they term style transfer generative adversarial network. Now let's turn to the conclusion of our presentation. The ability of GANs to generate infinitely many problems from the given data adds great value to the network, which is why it is being used in difficult problem domains. GANs do not lean towards estimation of distribution of samples. Instead, it generates data that resembles the actual data. Since the proposition of GAN in 2014 by Ian Goodfellow, this model has been getting a huge amount of consideration from the artificial intelligence world. A GAN typically contains a generator and a discriminator, which are prepared in a way that they move towards Nash equilibrium, as we discussed before. In my view, Keeping recent advancements of GANs and artificial intelligence in mind, the network can contribute immensely in the fields of parallel systems and in virtual real interactions. With the quantum computing and the quantum machines coming into the play, the generative ability of GANs coupled with parallel processing can do wonders of creativity. Thank you.